I organized this presentation in three main parts. The first two are very, very brief. So I'm just speaking a little bit generally about my research interests in terms of application, in terms of model methods. I have just 2 slides on that. Then I'm going to speak a little bit about a transportation system that I worked on, that has been a kind of a leitmotif in my research. I started working on these systems, then I stopped, and then I started again. And I think it's a nice transportation system. So I would like to speak about it without going too much into details, though, of the paper. I'm not presenting a specific paper, I'm just speaking a little bit about the system and maybe pointing out some of the difficulties into implementing the systems. And then I will focus a bit more on 2 works, especially one, let's say, and I just will say a little bit of words on another one. But both works are on a vehicle routing problem where travel time are stochastic and correlated. And in these 2, I'm going to go a bit more in detail. So just to make a brief survol of my research. So if we think about applications, I started working basically I started doing research on public transit, and mostly on-demand systems, such as everyone probably knows the GERAD system, and semi-flexible transit system. This system have several names right now: microtransit, demand-adaptive system, etc. And on this, I'm going to describe a little more later, so I'm not saying too much right now. And for freight distribution, I'm interested generally in city logistics systems. In particular, I worked on 2-tiered models where distribution, so in a city, there are some big distribution centers outside the city, and the distribution is done into 2 legs distribution. So there are some intermediate facility, which are called satellites usually, and this facility are potentially mobile facilities. And so the distribution is done with larger trucks from the city distribution centers to the facilities, and then with smaller vehicles into the city. And so I work mostly on tactical planning and on operational planning on this kind of problems. And then, of course, the core of a lot of these city logistic problems are vehicle routing problems. And so I'm interested, I'm still working on several variants of vehicle routing problem. One is with electric vehicles, where, just a reminder I'm pretty sure everyone here is familiar with vehicle routing, but just as a reminder. Oh, by the way, if you have a question at any point in time, that's for me. It's please just show your hand, and I will stop. So vehicle routing problems are in the basic version is a problem where you have a depot and you have a set of customer and you have a fleet of vehicles. Typically, vehicles are obviously capacitated, they have a capacity, and each customer has a demand, and you want to distribute the demand to the customer in such a way that the total cost is minimum, total travel distance, cost, it depends, it's related most of the time, is minimum, and each customer is visited exactly once. This is the basic version. Now, sometimes there are particular side concepts. For example, if the fleet is electric vehicles, well, in this case, unless you have a Tesla, you might have a limited range for your distribution. So one of the question is, okay, if I want to plan in-route recharges, where do I do it? And there are several variants of this problem with homogeneous recharge stations, or all the recharge stations the same, or some recharge stations are faster and potentially most costly than others, and you serve these things. So This is a family of problems I'm interested to. Then there are loading constraints. I worked on something called the fragility constraint, where basically you cannot put heavy items on the top, like heavy items on the top of fragile items, and your stock is organized as and your capacity is organized in stacks, for example. So there's some issues there, and in the third line, probably there's most of the research I did. It's variance of the city of the vehicle routing, where some of the data are stochastic. And this includes the Séminaire, let's say, the more focused Séminaire that I'm presenting later. And typical sources of uncertainty that have been focused on: service time, travel time, demand values, customer presence. And more lately, there is this new issues of autonomous vehicles, where some of the decisions might be decentralized. Like here in all for the previous 3 points, all the dispatch is done in a centralized way. What happens if the autonomous vehicles are free, in a sense, to choose what's going to be the next customer? So I have a PhD thesis on this ongoing right now on this. And I've been working a little bit on hydropower generation. This in collaboration with Hydro-Québec. We're working on planning planning the energy production for the short and medium term, for a network of reservoir. And the issue here is the water that arrives in the reservoir is stochastic, and you have some constraints such as the biological constraints or capacity of the reservoir, etc. So this gives a bit of a portrait of the major application which I worked on. And if we go more on the side of model and methods, well, many of the problems that are treated, that descend from the application I explained before, are basically decision problem with stochastic and dynamic data. So for sure, many of the approaches are based on stochastic programming, the stage, chance constraint, invariance approach, and the related solution methods are the classical one: integer, shape method, sampler average approximation, simulation, principal component analysis. And on this one, I'm going to speak a bit more today. And Markov decision processes that usually are solved by dynamic programming. In my paper, mostly in my work, I mostly tend to use approximate dynamic programming, in particular reinforcement learning. It's not a surprise, so most of these stochastic problems become large-scale deterministic problem. So it's not a surprise that I work a lot on the composition problems, like Benders decomposition, column generation, Lagrangian relaxation. And as we see in the Séminaire, some of those stochastic problems also are non-linear problems. So quadratic programming is something I'm interested to. I'm interested in working on this kind of problem too. Okay, so this gives a bit of a tour of the main, like where my expertise, where my research interests are. And now I would like to speak a little bit about this transit system. They're called semi-flexible transit system. When I started working on this, they were not really known. There were only a few people working on this. Then, as I said, right now there are more people are aware of the system. But still, I think those are interesting transit system, and they're, in my opinion, they're still not yet well known. And there's a lot of work to do on these. So let me start with some motivations. And if I can say, in the center of the city, anywhere where the demand for transportation is relatively high, the the traditional transit is usually quite effective. And why it is so? Because this is my reading, at least, because there's a large resource sharing. So there are many people sharing the same mean vehicle, and this lowers the cost per trip. And this allows the transportation company to provide higher frequencies, and so the quality of the service is better, is pretty decent in general, especially when the demand is high. But what it happens when the demand is low? And this could happen not only in suburban areas or in rural areas, but also in the city, in times where the demand is low, like such as night. And I always make this I have this kind of funny joke, in the sense, well, at least I find it funny, but let's say the quality of the service tends to decrease drastically because there's no much demand. There's not a lot of there's no resource sharing, if you want. So the service, it becomes less frequent, and so the quality of the service is less interesting. So people typically switch from public transit to private transit. So it could be Uber, could be taxi, could be bikes, could be whatever. So the idea is to for zones, let's say, where so semi-flexible transit system is an essay, an attempt to respond to this kind of situations. So what the semi-flexible line looks like. The idea is that even when you have a territory, and even when you have a low demand, so what happens is in some places you have a demand sometimes, but most of the time you don't have requests for services. Like there's no need for services in certain area regularly, but sometimes it happens. On the other side, there are some attraction poles. So, for example, it could be a metro station, could be a train station, could be a shopping center, could be a hospital. In these places, there is usually some demand. Basically, there's always some demand. So the idea behind the semi-flexible transit system is to have some stops that we call compulsory. There are stops in which the vehicle must pass. And the idea of these stops is to naturally capture demand, which is always there, that is always there. The idea then is that, so we have a kind of a basic structure of compulsory stop, each with a schedule. Now, the formal schedule, it's more general than a normal schedule of a public transit system, in which you have a time of passing. Okay, the vehicle is going to pass at this exact time. You have in this system a time window, which specifies the earliest service and the latest service time. This has some repercussion, and we'll discuss a little bit at the end about these things. The main idea is that this time window, in a sense, is used to potentially serve service areas which are called segments. So segments, which are these ovals, this ellipse there, are potential region that can be served on demand if you have some request. And the idea is that these time windows give some flexibility to the vehicle to do so. So in case, for example, there's no request, the vehicle would just move among a compulsory stop as if it was a traditional transit system. In case on-demand requests are activated, well, the vehicle would deviate from the shortest path between compulsory stop to pick up other customers. Now, of course, you can see here there are some kind of a conflicting objective. In a sense, we would like to give a lot of flexibility for the vehicle to be able to do deviation in case there's a lot of deviation. We would like to have large time windows because in this way, if the time, if in one segment I have more requests than the other, well, there is a way to make the time flow from one to the other. Like the time allocated to one segment can be scheduled for the other if the time window is large. At the same time, if the time window is large, what happens is that it happens that the people who use the system as a normal user, as traditional user, without reservation, going at the compulsory stop, well, this one might potentially have to wait for a long time. Now, this system, it's interesting for the structure, but I also think it's interesting because it can be, and it's what it makes the major difference with respect to the more flexible system, like a dial-a-ride systems, is that it allows easily to have, for example, a network of semi-flexible lines, but also to integrate with a traditional transit system, because one of the compulsory stop can very well be a part of the traditional transit system. And in this case, so there is a possibility to have a scheduled service that works as a feeder to the main system. And as you can imagine a little bit, there are a lot of things to decide here. Just if you think, here there's only one line, okay, but there could be many lines interrelated. And how could you, like at operational level, there are a lot of decisions to take. You receive a certain number of requests, which one you accept, which one you reject. Actually, what is your policy? Do you accept, reject, you postpone, what you do? How much dynamicity you allow into the decision making? Do you collect your demand, your request in advance before operation, or you collect it dynamically? And potentially the best option would be to collect it in both in advance and both dynamically, and how you update your plan, etc. This is so there's a lot there to do, and we're working with some colleagues on this, but also on the more structured system, okay? So it's more higher level, what we call tactical level, okay? Where do you put exactly your compulsory stop? Yes, where there are attraction poles, these are not always very well defined, but you also want to have compulsory stop in strategic points where you have connections. So those it's not so simple as saying, okay, let's put where attraction poles are, how you dimension your segment, how you dimension the region that you serve with one line, how do you decide how big are going to be the time windows, etc. So there's a lot of work, and I think right now, for example, we're working on a extension in which the vehicles are autonomous. So this idea of having compulsory stop might be relaxed, but let's say in the sense that the vehicle sometimes might not be there, just in case for some reason there's no request in that. But it has kind of become more a guaranteed service points instead of compulsory points. So there is a lot of work. And before switching to the next topic, I'm wondering if you have any question on this. Okay, so Jacques.
Do you work with requests on the day of operation?
Okay, so what we worked until now, until let's say a year ago, we were working on requests before. So we collect requests and then we do the operations. Right now, we're working on there's a PhD student working on this, on a system where a part of the requests are collected at the beginning, before operation, and we update the plan during operation as new requests arrive.
Okay, I've worked on that several years ago, and we observed that, say, if you take one vehicle, the duration of the operation for one vehicle is maybe fixed, say 8 hours. Then the 8 hours is split in two parts, the traveling time and the idle time. So if you minimize the traveling time, it is equivalent to maximize the idle time. Then we change the values of the time just by say, square. So meaning that if you have 10 minutes of idle time and another 10 minutes of idle time, square both. So 10 square plus 10 square, it is much less than 20 square. So 20 idle time is much more interesting than twice 10 minutes.
The idle time, what do you mean by idle time? Like, because
the truck is not, the vehicle is not traveling.
Okay.
It's not
the thing is that
it was just that the empty time, I would say, it gives about the same solution in terms of quality, except that now you have empty times that are larger. And then this was much easier to insert new requests on the day of operation.
Okay, I understand. Did you have time windows?
Yes, there was plenty of things.
Okay, because maybe the main difference here is that the time windows that are set at the compulsory stop are part of the design, if you want. So let's say it's in a sense the time windows are scheduled are done in such a way as on average the idle time is small. So we don't, at least for what we observe right now, we don't have a lot of idle times.
Okay.
But I would be curious to read more the paper and to see.
It's kind of a request by the schedulers. And
sorry?
It was a request by the schedulers to be able to fulfill new requests on the day of operations. So by doing our way, it was easier to find, oh, there's a spot there and there's one, and they were able to fulfill this on the phone. Yes, we
okay. Now I see. Now I understand what you mean. You mean that when you start taking a first set of requests, you're in your schedule, you're going to have some idle times because you still don't have the full. Okay, I see what you mean. I see what you mean. Okay, interesting. I'm going to have a look at the paper. If you send me the details, I will be happy to look at it. Thank you. If you have another question, otherwise I would go on the second pair of papers. Okay, so I'm going to go on. So this is a joint work with Borzou Rostami, is professor now in, I don't remember the name of the university, if someone can help. Guy Desonnier and Andrea Lodi, that I see they're here connected right now. Basically, in this presentation, I'm going to speak about two papers. One, we have been celebrating his appearance in operational research after a long itinerary. And the other one is still under review. And the second one is going to be mostly the main focus of what I'm presenting. So let's start. The talk is a bit is organized into, I have a bit of a motivations. Then I present this approximation scheme, which is the main topic of the paper, in which basically we present a principal component analysis technique to approximate the original problem. And then we show some application specifically to the vehicle routing problem and some computational results. So first of all, is it important to consider correlation when we have a decision problem with uncertainty? The answer is certainly yes. And it is important, for example, in transportation. And this is the case that concerns us the most. For example, travel time usually are very much correlated due to the congestion dynamics. In portfolio selection, for example, of course, multiple assets might be correlated. So when computing the risk of that, it's important to know that those assets are correlated. In facility location, of course, demand for several reasons could be correlated, seasonal or whatever. So the supplier needs to take into account about these things. Now, what happened is usually accounting for correlation instead of considering demand as independent, stochastic sources as independent, usually brings much harder problem to solve. Strangely enough, into the so the purpose of this talk is to try to develop approximation scheme for this kind of problems. And let's see a little bit about, so the main point here is that we are going to first present a general approach for addressing decision-making under uncertain and correlated data. And then we're going to a bit detail this on the vehicle routing problem. One of the particular thing here is that, particularly in the vehicle routing problem, there is not a lot of work done on assuming correlated data. So the main purpose here is to consider them and to develop an approximation scheme. Sorry for the repetition. Now, in literature related to the vehicle routing problem, so just because I didn't say it very clearly, let me just make a step back. So I said already what's a vehicle routing problem. In this case, we're focusing on a vehicle routing where the travel time are proportional to the cost, and the travel time is stochastic, and the cost and the travel time are not only stochastic but correlated among each other. Okay. Now, if you see in practice, when we see like from a descriptive point of view, it has been shown that correlation are very important in several networks, in several city networks, and there's some literature studying these kind of things. Also, there's some work done on okay, what if we forecast the travel time, the variance of a travel time can be underestimated by up to 75% when we don't consider the correlation. So neglecting correlation can be very bad for your solutions. So for decision making and correlated travel times, there is some literature, some on the shortest path problem, some on the Steiner traveling sameness problem. But to our knowledge, correlation between travel time has not been addressed in the vehicle routing problem. Actually, there is a work that is still work in progress, it's still under review, which, however, is consider a particular objective function, consider a make-span objective function. So in the next presentation, in the next time I present this work, I will put the reference here, even though it's not published yet. Okay, so what is our general setting? So how, of course, one can model correlation in many ways, in several ways. What is our choice here, our modeling choice? So we assume that we have a random vector, and we assume that we know that for each component of the random vector, we know its mean and the standard deviation, and we assume also that we're given some a covariance matrix. So a covariance matrix, of course, it's related to the correlation coefficients between each of the components of the random vector. How could we potentially theoretically retrieve this covariance matrix? Well, this is possible to, if we have, for example, correlations, we could relatively easily retrieve these covariance matrices through a well-known approach. That's briefly described here. Okay, so this is general setting. So the general model that we focus on is the following. So we aim at minimizing two components. One, it is a linear component. It's linked to the if you want, to the mean travel times, to the mean of the we're not speaking about travel time yet, but to the mean of the random variables. And the other one is more related to the interaction of the random variables. And the approach that we propose is actually valid for this kind of objective function, where I'm going to say in a second, Q could be 1 or 2. And the domain is linear at 0, 1, and linear. With different alphas can present, these values of alpha can present different, if you want, altitude risk. And if Q is equal 1, well, what you're paying is a convex binary quadratic problem. And the nonlinear term here is the variance term. And if Q is equal to 2, we have basically a second cone program with integrality constant, and the term here becomes the standard deviation. Okay. This model is known to be related to other ways of treating, to other models to treat uncertainty in literature, and robust optimization, value at risk, distributionally robust stochastic program. It's important to say it's equivalent to some specific case of these other kind of models, and these are can be found in the paper, in the second paper, which is also available as a cahier de GERAD. Now, what are the challenges here? Well, the matrix C, because it's a coloration matrix, is positive definitive. So in a sense, in theory, state-of-art solvers could solve them. However, it is generally very difficult to solve them, even for small size problem. And they are also not only NP-hard, but also hard to approximate. So we're dealing with problems that are very, 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 very difficult. Now, when we think a bit, if we focus a bit now to the vehicle routing problem case, our vector is travel times. They are correlated, and our purpose is twofold: to minimize the expected travel time, so the mu part, and we want also to minimize the overall time variance. The basic idea is that basically we're willing to pay a little bit more in terms of travel time if we can have routes that are less spread around, whose duration are less spread around the average travel time. Okay, this is a bit the idea here. The main important part here is this, I think, how to compute the variance of the route. So given a route, the variance is given by the sum of the interaction of all possible pairs of arcs. Okay. At one point here is important, maybe, to say is that routes, so arcs from different routes, don't interact. In a sense, the variance accumulates only for arcs that are on the same route and not from arcs that are on two different routes. This has an impact when we formulate the problem. So this is a formulation. This is it's to gain a little bit of space. This is a vectorial formulation. So we let's go a bit through the formulation very briefly. We have two sets of variables. There is one first set of variables that are 0, 1 variables for related to routes. So it's 0 or 1 if vehicle K chooses a certain routes or not. And we attach to this the average travel time. Then we need something to retain the arcs, which arc have been traveled by which vehicle. And this carries, if you want, the variance part. And so X are the second set of variables carrying the arcs. So in the constraints we have, of course, each customer needs to be served exactly once. This is the linking constraints, so the arc and the routes needs to be coherent, and each vehicle needs to be assigned exactly one route. Okay, so this is kind of a hybrid. We have a set partition formulation plus some arc formulation, arc variables. The important part here is that we have an index on the K. This is an impact. This is an index on the vehicles. Okay, so let's go a bit further. And okay, so this is a general formulation for the problem. And this formulation, we start working on this formulation in the first paper. So here, I don't go into the details of the first paper, I just explain a little bit what we do in that paper. So we first make a distinction. So between a full dense covariation matrix, in general, which we call general, and an adjacent matrix, in which we consider that only arcs who are adjacent to each other can be potentially correlated. So for the general case, we use the formulation that we have. This is basically we use that formulation, and we use column generation, and we have a master problem with quadratic convex objective function, and basically, but because it's convex, duality still holds, so we impose stationarity of the Lagrangian, we compute the reduced cost. And so we use a column generation there. And the subproblem is a classical shortest path, linear classical shortest resource constant shortest path problem, elementary shortest path problem. For the non-adjacent case, well, that allowed you to get rid of the K index and also allowed to use a different, we have potentially two reformulation, two approaches, but the one that worked better, it was a linear master problem in which, however, the quadratic, so we could reformulate the problem as a linear master problem, and we would deal with the quadratic part into the subproblem. However, the same approach was very difficult for the general case. So for the general case, worked more the quadratic master problem and the linear subproblem. So the point here is that we got fairly good results for the adjacent case, but for the general case, we're stuck to more or less 30 customers. So the idea is the main question that brought us to paper 2 was, okay, can we do something? Can we develop an approximation scheme for this in such a way that we can go towards higher, like we can address larger problems? Just getting a little water. Okay, so and here comes the principal component analysis. So what is the principal component analysis? It's a classical tool, and so we didn't invent anything. And the idea is, let's say that we have a set of data that are correlated in a sense. The idea, if you want, is to find a new coordinate system that allows, let's say, that transform the original space into potentially a smaller number of potentially uncorrelated variables. So, for example, here the idea is that, okay, there's of course some correlation here among the data, and in the new axis, in the new orientation of the axis, well, the x-axis capture most of the correlation between the points, the data. And let's say that you transcue, that you ignore the second component. Well, just the first component has captured, in a sense, a good amount of the variance. This is a bit the intuition behind. It is known that the best transformation. So the idea is that we want to find a set of perpendicular axes in which the first axis corresponds to the highest variance, the second axis to the second highest, etc. It can be shown that this can be obtained by solving the equation to find the eigenvector and eigenvalues. Okay. So basically, this allows us to open the door to a decomposition via eigenvalue decomposition. So it is known that because C is semi-definite positive, positive semi-definite, we can represent it. We can decompose it in this way, where U is a matrix R by M. M is the dimension of the space, and R is the rank of the matrix C. So this opened the doors to a reformulation, because if you define X new variables, so R new variables, one for each of the rank, as U times X, we can reformulate in a linear part a rejecting function as follows. So in practice, we can diagonalize the objective function. Now, in the corresponding program is the following. So we still have the X variables in the linear part. Now we have, in addition, R new variables, and they are linked to the, so we need to add constraints to link X and Y into the region. This forms a new a new feasible region. Okay, so in a sense, with new variables like this, it's not evident why it would ever be better. What is the main interesting part? Well, that if you take, let's say UL is the symmetrics corresponding, if you take only the highest, the top L eigenvectors of C, corresponding to top, so it's symmetrics of U corresponding to the top L eigenvector of C, well, you can write an approximation of the original problem. So this is exactly the same. This formulation is exactly the same, except that now, instead of having all the R components of the rank of C, you only have L components. So, but it's exactly the same formulation. And there are some interesting properties. Well, the value of this problem, so when you solve this problem, the value that you obtain, it is guaranteed to be a lower bound of the actual optimal value. So this is very interesting. So if I consider a subset of the components, I obtain a lower bound of the original problem. Not only, there is a monotonicity property. In a sense, more are the component that I add, closer I get to the original problem. Of course, more complex becomes the problem to solve. Not only, on the other side, if you see here, the original constraints are retained into the new formulation. So we didn't lose any of the constants in the original formulation. So basically, what happens that the solution of the approximate model also give us an upper bound. It's a feasible solution for the original problem. So it also gives us an upper bound on the value of the problem. So basically, we can build optimality gaps. So when we have a solution, we can already say we know how far we are in the worst case from the optimal solution. We actually also developed some worst case bound. And what this worst case bound is saying is that basically, well, let's say the value. So let's say if you obtain a solution from the approximate model, and we plug it in the original Bezier function, what is its value? Okay, but this is val XL. Well, what it says that this is guaranteed to be within a certain epsilon to the optimal solution. And this epsilon is this expression here, where alpha is the weight in the objective function, lambda is the largest ignored eigenvalue, and m is the dimension of the space. So in theory is huge, but actually what m is, if you go in the proof, is the number of solutions that are non-zero. And actually, for the Baker routing problem, of course, the number of variables that are non-zeros. Of course, in the Baker routing problem, the number of variables that are non-zero is much smaller than the entire space. Now, of course, not of course, but I don't have a table on this, but then we'll see that the actual empirical bounds are much better in any case with respect to the theoretical bound. But yeah, we have also theoretical bound on this. Now, just to also have a comparison with some other approximation scheme, we also build a much simpler approximation in which we call like a linear approximation. Like, assume we have a feasible solution X. Well, the nonlinear part is convex. It's a convex function. So basically, as simple as that, we can the nonlinear part, the convex part, can be underestimated by a supporting plane in X. So we generate we could potentially given one feasible solution, we can generate just one lower bound, one supporting upper planes, and basically reduce the original problem into a linear one. So this is just to have a comparison with a potentially naive approach and to see what happens with that one. So just as to bring back together the major ideas here, this is the original set partitioning formulation. The parts in blue are in blue because they're going to change in the next slide. So this is the original set partitioning formulation. With the reformulation, we, so PCA-based approach, we have now new variables y, and these y's are linked to the z. Now, the interesting thing is for the specific case of the Baker routing problem, what is it is interesting is that the x variables that were carrying out information about the correlation, well, are not in the model anymore. So those basically the y's variable are substituting the x variables in this part. Yes, the x part of the variables in this new formulation. And so you now start understanding why it's particularly interesting for the case of CVRP to use this kind of approach. And instead, for the linear approximation, the model is simply, so we have a linear objective function, and where G is the subgradient obtained at one given feasible solution. Okay. And this is basically a classical CVRP with a heterogeneous fluid. Okay, so we solved both these algorithms. We developed branch price and cut algorithms. For the PCA, we basically, the major structure is the same as for the original problem. So we have a master problem with this quadratic a convex objective function. We impose the linearity of the Lagrangian. We find the reduced cost, and the subproblem is a classical simple elementary shortest path problem with resource constraint. And for linear approximation, it's linear master, linear subproblem. Of course, and we use GENCOL, so there are a number of acceleration techniques implemented into there. I'm not going to go into the details. I think I'm a bit tight with the time. Tests. Okay, we used the VRP Solomon's instances, the three families, without time winners. Mean is being chosen proportional to the cost. We have a procedure to generate the random variable. We have a coefficient of variation from 0.01 to 0.2. And then I'm going to skip, like it's a bit complex the way to generate, but the thing is that the way we generate the covariance metrics, we need to ensure in the procedure that the metric is symmetric and positive semi-definite. And for the parameter that we've been testing, we have alpha, which is the relative weight in the objective function between the linear and the variance. So the expected and the variance, we took these 5 values from 0.01 to 0.5. And for number of components, considering the approximated model, we consider 1, 5, or 10, and time limit of 5 hours. Okay, so let's have a look at the results briefly. Okay, so what we have here. Here we have a case for alpha equal to 0.1. Here we have the number of customers. In the first column, we have the exact approach that was developed in the first paper. And second, third and fourth groups of column, we have the approximate approach with 1 component, 5 component, or 10 components. Now, if we go a bit more into details of the results, what is it doesn't always happen, but let's say in this case it happened that even with one only component, we actually found the optimal solution of the problem. Okay, so if you see, so 1 with L equal to 5 L equal to 10, we both in all cases we found the optimal solution. But for all cases, we could go and solve instances with larger number of customers, larger instances. Sometimes here, for example, in the last column, you can see that the L5 and L10 could find a better solution than the one with only 1 component. When you see about the computing time, well, we see that the difference is impressive. So of course, larger are the instances, the more complex become to solve the problem. But with respect to the exact approach, of course, the reduction in computing time is drastic. And for the gaps, so now what is interesting is that when you have more components, you can build sometimes better gaps, empirical gaps. So for example, here, the gaps are slightly better than the one with 1 only component. Okay. Now, it's just someone is texting, is chatting. Oh, okay, sorry. So now, of course, things change a little bit, but so now I'm showing one. I've the detailed other results, but basically the major point is that more alpha is high, higher is alpha. In general, more difficult are the computing time increases, and of the 3 sets of instances, R101 tend to be more difficult. But the overall behavior, what we observed, more or less, is the same for all settings. And now this is a comparison with the linear approach, with the, if you want, the naive approach. And here we have here in this case we have the instances on the top. Sorry for switching the direction of the table. But let's say so. Here we have so we have all the three instances family C, RC, and R with all the number of customers. Here we have the upper bound and the computing time of I think it is the linear, the quadratic, and these are the comparison between quadratic and travel time. So and quadratic and linear approach. Oops. So here, what it is, so basically, when it is positive, it means that the solution of the quadratic was better than the solution of the linear. So what you observe that sometimes the linear makes a good job. Sometimes, even if it's a relatively naive approach, can find solutions that are not too far from the one that the quadratic found, but not always. For example, here for R101, well, the gaps start becoming much worse. Okay, we don't know why this happens, but in general, these instances tend to be more complex than the other one. And as for the computing time, here positive number, like a higher than 1 number, means that the quadratic is slower, and of course, as expected, the quadratic can be slower. It's a much more complex problem to solve. Okay, so and then if we I have some graphics on this is what we call the price of robustness. So let's say now that for alpha equal to 1, so we have basically in the relative weight between objective function, component of the objective function, we have 0,9 to the linear part and 0,1 to the variance. What happens with respect to the increase of the objective function with respect to the deterministic case? Well, what we see, the increase of the expected travel time with respect to the deterministic case. Well, what we see is the following. We have for the C, for the R, the increase into the expected travel time is around 2 and like 0%. You have here is dark is the quadratic, linear is the white is the linear. So in both cases, you can see that the tendency is in common, but let's say that the increase in expected travel time is pretty low. For the R, and the difference is like the average increase increase in expected time is 15% for the quadratic and almost 20 for the linear. What it is the impact on the reliability? So again, with alpha equal to 0,1, what is the impact on the reduction of the variance of the routes? Well, the reduction in routes is pretty drastic. For example, we have around 70% here for the QC instances, around 40% for the RC instances, and 75 around for the R01. So now the interesting thing is that the alpha can also be used as a way. Let's say for in this case, let's say that for the R instances, with alpha 0 equal to 0.1, the increase in expected travel time was, let's say, too much. Alpha allows to moderate this behavior. And for example, here we have an experiment on the R with alpha equal 0.01. And okay, so with this value, the expected increase in travel time is a little bit higher, with a significant reduction of the variance. Okay, so I think I'm kind of conclude this part very briefly because I'm out of time. And well, I would stop here, and maybe I would keep open for some question if there is any. Thank you for your attention.